So we left off here, we were looking at the mechanics of breathing. And we're going to kind of quickly summarize all of that. We'll start by summarizing Boyle's law and how that influences the mechanics of breathing. And then we'll kind of draw out the pressure gradients and speak about inspiration and expiration. Okay. So just reviewing Boyle's law here. Boyle's law, we said, was the specific application of the ideal gas law within our physiology. And so what it basically says is that for a given quantity of air, right? So for a given quantity of air in a container, pressure is going to be inversely related to volume. Right? In other words, if volume of the container goes up, pressure within the container goes down. Okay, and the reverse is true. If the volume goes down in that container, and this applies to a lot of other things that we probably don't even know. The deployment of airbags is an application of this law. Things like spray cans are an application of this law. If we change the volume, we can manipulate the pressure. Right, so decrease in volume of the container will increase the pressure within that container. Okay. And so just to make a note here, pressure changes in response to change in volume. Changes in volume. And so this really ties into what we were saying last time, that it's really kind of this domino sequence of events, right? I'm going to change the shape of my thoracic cavity. So the first thing that happens is those muscles are innervated and they change their shape by contracting. So that changes the volume of the container, which is our thoracic cavity. Then we manipulate the pressures in order to manipulate our gradient, and then we can have airflow. So what's responsible for these changes in volume are going to be the respiratory muscles. So the respiratory muscles change the volume of the thoracic cavity. And as a result, the pressure changes. Okay, so this is how Boyle's law applies to our physiology in terms of changing the shape of the thoracic cavity, thereby changing the pressures and manipulating airflow in and out. Okay. All right, what we'll do now is kind of look at let's look at how those gradients are created and how they differ for inspiration and expiration. So it's kind of a view, or we call pulmonary ventilation here. Oops, okay. So the first thing we want to make a note of is what drives ventilation, right? The driving force for ventilation is our bulk flow. In other words, our pressure gradient, okay? So the driving force for ventilation is our pressure gradient. So it's going to be the difference in pressure. And another way to represent that is our atmospheric pressure minus our alveolar or intraalveolar pressure. Okay. Another thing we want to make a note of here is that if there's no gradient, there's no movement of flow. In other words, at rest, the atmospheric pressure is equal to the intraalveolar pressure. Okay. All right, so let's start by making a note of what atmospheric pressure is. So atmospheric pressure, we said, had sort of two different values. It was 0 millimeters of mercury, according to the way that physiologists sort of made that the set point. Because of the variability with altitude, we said that the relative value is 0 millimeters of mercury. But then we also described the absolute value, which was at sea level, which was 760 millimeters of mercury. Okay, and I've seen questions in your book that reference both of these values, so make sure you know both of these values. Although when we speak about the actual movement of flow, we usually just zero out our atmospheric pressure and speak about the other pressures relative. I'm still going to include the absolute value so you have that as a reference point, because some of your questions do reference that absolute value, and it will say specifically absolute versus relative to indicate which of these two is the required response, okay? So let's draw two scenarios here, one for inspiration, one for expiration, and talk about how our pressures change in order to accommodate airflow. Okay, so let's draw a human here, or a human-like figure. Please excuse my drawing, guys. And let's draw another one over here. All right, I give up. Okay, so we have air coming in through the nasal cavity, through the oral cavity, communicating all the way down to the lungs. We've got our left lung, or our right lung, excuse me, and then our left lung here. Right, same thing over here. Left lung, right lung, left lung, okay? Now, what is the state of the diaphragm in respiration? What is the state of our diaphragm in respiration? Excuse me, in inspiration. Kind of mentioned this before. It's flattened, excellent. It's nice and flattened out. So during inspiration, you have this nice flattened diaphragm, okay, which we know is helping to increase the volume of the thoracic cavity and by extension, manipulate those pressures. So I'm seeing other responses here, not curved or relaxed. It's actually not relaxed, it's contracted when it's flattened out that way, okay? So it's contracted and flattened out. Whereas in expiration, it's curved and this is its relaxed state. Okay. All right, let's label out our pressures here. So we know that the reference point we're given is 0 millimeters of mercury. And so if alveolar pressure needs to be lower than atmospheric pressure, right, to create that high to low gradient, the pressures during inspiration in the alveoli are going to have to be negative, right? So our intraalveolar pressure is going to be -2 millimeters of mercury. And then we're also going to put the absolute value here. So 760 minus 2 millimeters of mercury is 758 millimeters of mercury. Okay. So I hope everyone can see that although we're thinking about absolute and relative, both of these values are less than what's happening out here in the atmosphere. Okay. Let's think about our intrapleural pressure. So this is our pleural cavity or pleural sac. Right, although it looks nothing like this, it's a much smaller space. That's the representation of our intrapleural cavity. And let's talk about the pressure that's found there. So it's going to be, again, it must be more negative than what's happening in the alveoli in order to keep that negative pressure and keep those two structures adhered. So in the intrapleural space, the pressure is -6 millimeters of mercury. Okay, there's that -4 differential. Or 4 millimeters of mercury differential, excuse me. Okay. And we talked about what this difference is, right? This difference is our transpulmonary pressure. We'll talk about that a little bit later on, but alveolar pressure minus intrapleural pressure is our transpulmonary pressure, is our distending pressure, okay? And then the absolute value here is going to be 754 millimeters of mercury. Again, a 4 millimeter of mercury difference. Okay. And so in other words, what we see is that the atmospheric pressure is greater than the intraalveolar pressure. And so our differential here is going to be negative. In other words, we're going to have inward airflow. Okay. Can everyone see that? So someone is asking, why is it a negative pressure? It's a negative, which space are you talking about? I'm not quite sure. But all of these values are negative because that is what would, that's what would be conducive for airflow. If our atmospheric pressure was setting it at 0, remember, we talked about the fact that physiologists kind of simplified all of this, right? We have relative atmospheric pressures depending on our altitude. And so physiologists said, let's just set this at 0. And then we can describe what's happening in inspiration relative to that 0. And so that's where we get these negative values from. If it's less than 0, they have to be negative. But in terms of the absolute numbers, they're actually pressures. They're actually not negative. Okay, I hope that makes sense. All right. So -6 here is just a representation of what intrapleural looks like in comparison to the 0 millimeters of mercury that we set as our relative set point. All right, but in actuality, the pressure in there, if you were to put something in there and measure it, it's actually about 754 millimeters of mercury. And again, that can vary depending on where you are in terms of your altitude. If you go way the top of the highest mountain, it's going to be really low. And if you go below sea level, it's going to be really high. So these numbers are actually fluctuating depending on where we are. And so just setting the atmospheric at 0 and then thinking about the others relative to that is a simplistic way of looking at these pressures. Okay, so everyone with me so far? Here for inspiration, we have a higher atmospheric pressure than what we see in the intraalveolar space. And so because this is a negative value, right, 0 minus this value, it's going to accommodate inward airflow. Okay, let's look at expiration. So in expiration, we have higher pressures. Again, thinking about that 0 as our relative value, our intraalveolar pressure is now +2 millimeters of mercury. Okay, and in terms of the absolute value there, we're just going to add 2 to our absolute figure, so about 762 millimeters of mercury, if we're at sea level, that is. Okay, and then in the intrapleural space, remember, there still always has to be more negative than what's happening in the alveoli. So the intrapleural pressure here is going to be -2 millimeters of mercury. okay? And again, thinking about our absolute figure for that, our absolute value, that is 758 millimeters of mercury. Okay, everyone with me so far? Can we see how these pressures are changing for inspiration, then for expiration relative to that zero? Let's just label the diaphragm here. Okay, let's see. Someone's asking, are these fixed numbers? I'm not sure fixed in what sense, but one, these are variable numbers, right? We talked about respiration as being a very flexible activity, a very malleable activity. So pressure goes up until we've achieved our gradient, and then it drops until we get our rest, up until we achieve our gradient, and then drops. So these aren't fixed at any one point during respiration, and they also aren't fixed in the sense of our altitude. Okay, I'm not sure what fixed in what sense, but they're not fixed in terms of stages of respiration. They're always changing. And they're always changing if we are changing our altitude as well. Okay, and that's why it's so important to sort of zero out the atmospheric pressure, because things can get so complicated if we're thinking about whether we're at sea level, below sea level, how high, how low, you know, in terms of referencing that sea level pressure there. Okay, and so if we think about our differential down here again, what we see is that the alveolar pressure here is greater than atmospheric pressure, which is what we want. So that's going to be a positive gradient. In other words, we are going to see outward airflow. Okay. All right, let's talk about what happens at rest. Now at rest, what we see is the pressures sort of meet in the middle. So they go from -2, right? So -2 in inspiration, all the way to +2 for expiration. And so at rest, remember, in order for there to be no airflow, the pressure has to be 0. So at rest, let's kind of put that in the middle here. At rest, alveolar pressure, intraalveolar pressure is equal to atmospheric pressure, which is equal to 0. Okay, and so there's no airflow. All right, and then the final thing we want to say here is that value that we described as the transpulmonary pressure. So transpulmonary pressure which again is usually always changing with the various stages of respiration, but usually it's also described as distending pressure, the ease with which the lungs want to distend. Okay, and so we describe it as being the alveolar pressure, intraalveolar pressure, minus the intrapleural pressure. And so if we think about, it can be different on this end and different on this end, but when it's the highest is during inspiration. That's because the lungs really want to distend during inspiration. And so if we think about alveolar pressure being -2, intrapleural pressure being -6, that's going to end up being 4, okay? And so that's going to be its highest value. So the transpulmonary pressure is going to be 4 millimeters of mercury during inspiration. And then as the intrapleural pressure increases, the transpulmonary pressure is going to decrease and this value will change, okay? And so that's going to make it harder for the lungs to distend during expiration. So during inspiration, we have 4 millimeters of mercury, and that's going to be in favor of distension or inspiration, which is happening during that phase. Okay, But the important takeaway point is the relationship between the intrapleural pressure and the transpulmonary pressure. If intrapleural pressure decreases, transpulmonary pressure increases. So I'll put that over here. So if you have a decrease in intrapleural pressure, that is an increase in transpulmonary pressure. And if we have an increase in intrapleural pressure, that is a decrease in transpulmonary pressure.